Okay, welcome back. Okay, I think the caffeine or the tea has stimulated our brains, and we are ready for the next session on neuroscience. Okay, may I invite Dr. Lui again?
So welcome back. Let me introduce our third speaker, Professor Andrew Tolmie, who is the Chair of Psychology and Human Development at the UCL Institute of Education, University College London. He's the Deputy Director of the Birkbeck UCL Centre for Educational Neuroscience and Program Leader for the joint MA-MSc in Educational Neuroscience. So one of the first programs in the world. He was editor of the British Journal of Educational Psychology from 2007 to 2012. He's a developmental psychologist with long-standing interest in the growth of children's implicit and explicit conceptual representations, their behavioral skills, and the relationships between these, especially for primary school range age. I think you'll find that you can tap on Professor Tolmie's wisdom on the learning of science with respect to this implicit explicit conceptual representation. So most of his work has been focused on educational relevant topics and settings with a substantial emphasis on science learning. He's a member of the Royal Society, working group on reporting on math and science education on ages 5 to 14. So let us invite Professor Tolmie to share with us.
We need to jump about a bit, or I think I do anyway. Let's get this the right way around. So I'm going to be talking about science learning and adopting this kind of perspective. I think that I should say to start off with, though, that the flavour of this talk might perhaps be a little different from those of Songil's and Roy's, in as much as we're in a different kind of state of development when we think about the applications of educational neuroscience within science learning, because it's a much, much less developed field. We have much less in the way of detailed evidence to go on, and that's meant that in many senses we've been having to work really at kind of drawing some inferences from the neuroscience work that does actually exist and trying to piece that together with the behavioural work that we already know something about. And so it's a kind of, an amalgamation really of those kinds of things that I'm going to be talking about this afternoon. But I think actually a further point to draw from that is that maybe this is quite a good example of what the developing application of educational neuroscience might look like in areas where there hasn't been so much in the way of developed application previously. So it might give you, in a sense, a kind of flavour of what this kind of work might look like as it moves forward in other areas that are less researched. So anyway, let's kind of move on and see what you make of this story. So I love this photograph, actually. I don't have any particularly good reason for including it in this talk, except that I really like looking at it. It's just the kind of degree of enthusiasm and engagement that's shown by these kids as they're kind of operating with this. I've never actually also been quite sure exactly what's going on down here at the bottom, but maybe we shouldn't inquire too deeply. Okay, so learning of science. Let's think about this in terms of what it might be if we're trying to think about the objectives of teaching science, what it might be that we want children, learners to actually be able to come away from this experience with. And there are various different kinds of conceptualizations that people have of this. But I think at root, and I was interested actually that the kind of dimensions that I'm kind of pointing at here, especially these later ones, it maps on beautifully to what Roy was saying about the kind of neuro-understanding, neuro-prediction, neuro-intervention. And I'm glad that's true, because it ought to be true, actually, that if we're talking about how science knowledge is actually kind of generated and what it's composed of, it is exactly these kinds of dimensions. So at a kind of root level, we've got some very kind of basic things to do with observation and being able to capture data about events. But just observation on its own won't take us too far. That's probably the kind of thing that our deep ancestors were quite good at. But what they probably weren't so good at was things to do with description and explanation. So it's not just about observation, it's about being able to capture the characteristics of important events in explicit terms, use of language, which enables us to actually kind of then be able to talk about those, share those observations with other people. So it's about capturing and portraying phenomena in simple terms, accurate terms, but explicit terms. And then at a kind of level beyond, at a level beyond that, we've got explanation. So it's not just about describing events, it's about being able to explain what actually connects events. So how does one particular event lead to another? So we're talking about the idea of causal relationships between events and trying to understand something about what the mechanisms might be that join these things together. And then once we've kind of built up something of this kind of stage of understanding, then it becomes possible to do things around predicting events in future on the basis of our causal understanding, be able to think about what might therefore happen if we observe a particular event which has been associated with a particular outcome previously, then we would anticipate that that will be something that will happen again. And then if we get good at being able to predict things accurately, then we can move on to start to control them and actually manipulate them. And of course, part of what's going on here is the kinds of things that we actually do when we're doing a lot of science is about kind of setting up tests, experiments that enable us to predict outcomes and then try them out and see whether those events actually turn out the way we expect them to. So those are the kind of basic dimensions, if you like, of learning science and what it involves. And I think I'd like you to kind of take a few kind of general messages away from that in terms of the key characteristics of what we're talking about here. Firstly, there's an emphasis on causal processes that is common really to any particular kind of area of science. So it's about cause and effect, and it's about trying to understand the processes that connect those things. It's about trying to develop explicit concepts, things which are language-based that enable us to capture those causal processes, predict them, explain them, but above all, that's the basis for shared analysis of events. It's about being able to discuss our understanding with other people, share that test conflicting models, etc. The key thing is that science is not private understanding. Science is shared understanding with communities, and it therefore has to be something which is embedded in explicit ideas. Okay, and then the third kind of key dimension is this idea of being able to actually not just be able to kind of capture events in language and be able to understand something about their characteristics, those causal relationships. It's about being able to generate evidence to test these things out. So it's about this process of applying tests, seeing what happens, explaining those to make sure that our understanding is accurate. And that's what we generally tend to refer to, particularly in the kind of developmental psychology literature, as scientific thinking. Okay, so there's three things really are kind of fundamental to learning science: and understanding of causal processes, building up explicit concepts, and understanding something about scientific thinking. Okay, so if we've kind of mapped out the territory in that kind of way, then the obvious question is really what do learners understand about these things at different ages? It's that I kind of want to kind of pursue next and think about what we know about that and what that tells us. And one of the kind of key things here is that that actually when we look at some aspects of this, it seems like children are really actually quite good at a lot of this stuff. In particular, there is a relatively kind of good amount of evidence that children show sensitivity to causal connections between events from a very early age, certainly prior to the acquisition of language, and possibly innately. I think that's a little less clear as to whether that's true. But certainly it's from very early on. So some of the evidence for this has come from studies using what we call, I'll show you examples of these in a moment, what we call direct launching, delayed launching, and non-contact events. And the kind of key thing from this is that actually children from the age of infants from the age of about 6 months, though not younger than that it would seem, responds to direct launching events only in terms of causality. And let me show you what these look like. So this is my rather wonky attempt at an animation. I'm afraid my skills at this are not as well developed as they might be. So you'll have to bear with me and kind of extrapolate a little bit as to what this should actually look like. But the kind of main thing is that what we've got in these events is we've got just simply two geometric blobs. And in a direct launching event, what happens is that the first blob moves across the screen and the second blob more or less instantly moves away from it once it's made contact. Okay, so that's a direct launching event. This is a delayed launching event, so some similar kind of idea, but this time there's an appreciable delay, a greater delay than there was in the previous one anyway, between the first object making contact and the second one moving away. Okay, so that's delayed launching. And then a non-contact event, you can probably anticipate what this is like. The first blob moves, it doesn't make contact, and then the second one moves away. So how do we do this kind of research to think about how infants interpret this? The kind of standard technique for doing this is using what's called a habituation paradigm. I don't know, some of you may be familiar with this, but let me just kind of give you a brief explanation for those who aren't. So the basic idea, of course, you can't ask infants much about what's going on because they can't respond. So you have to kind of infer from their behavior what might be happening. In habituation paradigms, what we're doing is we're making use of the fact that infants get bored with things pretty quickly. And so if they see something that is actually apparently to them the same thing over and over again, they just get bored and they won't pay any attention to it. And we can use the fact that if their attention reawakens, it must be therefore that they have actually spotted something new, different, surprising about the event that they've been exposed to. And the key thing about these different kinds of launching events is that if you reverse them, which is what was done in the habituation studies by Leslie and Keeble, if you reverse them, so you kind of habituate them to these first motions as I've shown them to you, you reverse them. If you reverse the non-contact event, they don't pay any attention to it. So they're not seeing that as different. It's just the same kind of event. If you reverse the delayed launching event, again, they don't pay any attention to it. They're not seeing anything different. If you reverse the direct launching event, their attention reawakens. And that suggests they're seeing something different when that sequence is reversed, which has been interpreted as indicating that they are understanding a causal relationship and are surprised when that causal relationship has actually been transformed into something that works the other way. Okay, now there's a bit of a stretch of imagination in that, but certainly there's something to be explained there as to why they treat that particular reversal differently when there's contact and immediate effect involved. Okay, we're a bit more confident about what's happening a little later as children are first beginning to become adept at using language. And again, it's a similar kind of picture, really. So if you show children from about 24 months on this thing called the Blicket detector. What's a Blicket? Does anyone know? It doesn't exist, actually. It's a completely made-up idea. So there is no such thing as a Blicket, but however, children are told what we're going to do is we're going to play a game where we're going to find out Blickets, and we're going to have these different objects, and we're going to place them on this thing, the Blicket detector, and if the music plays when this object is on it, it's a Blicket, and if it doesn't, then it's not a Blicket, okay? And what happens in this particular kind of study, of course, there is no real Blicket detector. This is all being manipulated by the experimenter. But basically what happens is they're shown a series of objects that set off the Blicket detector and others which don't. And they combine different features, and what they've got to do, in a sense, is to work out what are the critical features that are setting off the Blicket detector. Now, they're not asked to describe that explicitly, but what they are asked to do is they're shown a series of trials of that kind, then they're shown some new objects with different kinds of configurations, but utilizing some of the kind of features that they've seen previously. And they're just simply asked to say, is this going to be a Blicket or isn't it, or is it not a Blicket? And their accuracy at predicting what these things are, what the pattern is that's going to set off the Blicket detector, their accuracy from 24 months is more or less perfect. Okay, so they're really good at doing this. And what that must mean is at some kind of level, they're actually extracting causal associations from the events that they've seen. They're extracting the key patterns from that, and they're able to then forward apply those and make predictions to subsequent events on that basis. Okay, so that's at 24 months. They look still then pretty good. And in terms of, so that's about the kind of observational side of things. They look pretty good at that. In terms of this kind of idea of scientific thinking, again, the evidence is it's a little bit later, but certainly from towards 4 years, children, once they've seen a particular cause-effect relationship, particularly if the evidence about what's actually going on is somewhat ambiguous, and therefore there's some kind of clarification needed. There's a range of studies using that kind of idea in lots of different ways. What they will do is they will be very much more likely to make interventions, manipulations to test out those relationships and actually find out what the true state of affairs is. So I don't want to go too much into the detail of those studies, but basically, again, by the time they got towards 4 years, they seem to be quite adept at making manipulations in order to uncover subsequent information and get some evidence from that. Okay, so if we take those kinds of pieces of work as a whole, what that seems to suggest is that the early scientific abilities that children have are really quite good, which begs some interesting questions, if that's true, about why they then struggle with science learning in school. And in actual fact, we've been thinking about this for quite some period of time. And of course, the point is that we're not necessarily talking about the same kinds of things. So the kinds of things we might be talking about with infants, young children, are perhaps more analogous to the ability that it takes to catch a ball. So all of you probably are relatively good at catching a ball. Some of us are better at it than others. Some of us have more recent practice, I guess. But all of us have got, are able to make a reasonably good stab at how to catch a ball that somebody's throwing to us, which means that we're quite good at understanding what the trajectory of that ball is going to be, where it's going to be when, and move ourselves in order to actually do that. If I then subsequently asked you, having shown you can catch a ball, to describe what the pattern of motion was, you're probably not going to be very good at doing that unless you've actually had some kind of particular training in thinking about the kinds of ways of formalizing that. So these things are not the same. One is a relatively kind of tacit understanding that enables you to make some actions that are kind of appropriate for those circumstances. That's not the same as something which is to do with a more explicit understanding and a more systematic testing of ideas, hypotheses, and explanations. And in some of our work about, I hesitate to say it, about 20 years ago now, which is almost staggering, we looked at this in a lot more detail. And this was with 9 to 14-year-olds. And what we did in this particular study, quite detailed work with about 120 9 to 14-year-olds in total, what we did was to test out their understanding of 4 different areas of physics. So forces, shadow size, water pressure, and motion down an incline. And we simply asked them, first of all, we went through a kind of pre-test where we asked them to just simply kind of indicate which factors they thought affected outcome in each of those different areas. Okay, they didn't see anything about what actually happened. They were just asked, if we change things in this way, is that going to make a difference to the outcome? Yes or no? And we collect observations across a series of trials in that way. And that gives us some sense of what their beliefs are about how things should actually kind of be affected by changing different factors. And then we asked them, in a subsequent stage of the study, we asked them to demonstrate that their beliefs were actually correct. So you thought that how high the car started up the slope would make a difference to how fast it would roll down it. Do some tests to show that's true. And what we found was that even at age 14, they were really bad at doing this. Very, very few kids. It did get slightly better as they got older, but very few kids could make anything like a controlled test to find out how a particular factor operated. And having confused things by not doing controlled tests in the first place, They were then very poor at actually kind of making any systematic prediction about outcomes, about observing the outcomes, about trying to interpret those. So the whole thing basically descended into a kind of chaos. And yet, right in the background of all that, the point that I've really kind of been drawing attention to in the first part is that their awareness of what factors actually affected outcome was really, really good. So across something like about 1,500 observations, we only found 4 instances in which children thought that something that did affect outcomes, they believed that it didn't. So if something genuinely affects outcome, they knew that, they all knew that. And this wasn't something that would happen during the course of our particular study because we were giving them no feedback, and moreover, we were using topics that they wouldn't at that stage of the curriculum have actually covered in class either. So somewhere along the line, they picked up really sensitive information about what factors operated in each of these 4 areas. They had really good understanding of that, and yet they couldn't do anything like a controlled test to actually show that that was what was going on. Okay, so it looks like, on that kind of evidence, and this is what we've been working on more recently, that there's some kind of separation between this kind of pre-verbal awareness that we were looking at first of all and explicit knowledge. And that's actually kind of a source of difficulty for children's science learning. And there's some evidence from, and this is where the neuroscience begins to come in, there is some evidence from some of the kind of neuroscience work with adults that actually suggests that this may indeed be true. So this is data from an ERP study with adults. So ERP is an EEG technique where basically what you do is you have a kind of marker event and you track the electrical activity in the brain immediately following that kind of marker event to see what happens. Okay, so that's the kind of general notion of this. So in this particular study by Calais and Rayner, what they did was to show adults animations of that were involved in a trajectory task. So we've got an object, a ball, exiting 2 different types of tube. One tube is kind of spiral, and the other tube is straight. And they see the ball exiting the tube either going straight on and down or continuing around in a curve, and they see both those options from both types of tubes. So we've got 4 types of event, basically. Curved tube with straight motion, curved tube with curved motion, straight tube with straight motion, straight tube with curved motion. Okay, so what they were asked to do was to simply say whether they thought each of these events as they saw them were correct. Now, I'm not going to test you out at this particular point in time. It is a very, very common belief that people have that when something's been traveling in a curved path, it will continue to do so once it's free of constraint. Go and test it out and you'll find that's wrong, okay? Yeah, that's not how it works. Once the object is released, it simply has forward momentum and gravity is operating to kind of pull it down. So it will always have this straight trajectory. So what they did was to ask the participants to say which of these which looked correct and which didn't. And in terms of their responses on that, the behavioural judgments just made via key press showed exactly that kind of error that's very characteristic. They tended to think that when the motion was from the curved tube, that the motion would be curved, okay? And when it's a straight tube, it would be straight. But the interesting thing was, in terms of the measurement of the electrical activity that was going on at the same point in time, what they found was that there is a kind of peak of activity that occurs at a point on the kind of time span immediately following the event, which has, from a lot of mapping work in other EEG type studies, has been regularly associated with semantic violation. So basically, you get this peak when you see something that doesn't look right, okay? And what they found was that they got this peak, sorry, press the wrong button. They got this peak, whether the motion was from a straight tube or spiral tube, only for the curved motion. So at some kind of level, the participants' brains, if you like, were telling them curved motion, not right. But behaviourally, they were responding as if curved motion from a curved tube was right. So we've got two different things going on depending on which particular type of response you're paying attention to. Okay, we get a similar kind of thing from behavioral studies with 6 to 10-year-olds. If nobody's kind of mentioned this previously, I don't think I have, it's really difficult to do this kind of imaging type work with young children because they don't stay still enough to enable you to get an uncontaminated observation. So actually we tend to rely a lot more on behavioral data with children for that reason, though these techniques are getting better and increasingly I'm hearing about studies where people have got very young children to sit still in an fMRI scanner, which I don't know if that involves sedation, but I think it's the only way I can think it might be happening, actually. Anyway, so behavioural studies with, this is a study by Christine Howe and colleagues at Cambridge with 6 to 10-year-olds. And it's a similar kind of idea to the Callahan Rayner study, though without the ERP element to it. And what kids in this particular study were asked to do was to watch this balloon floating gently across the Cambridgeshire countryside with a young girl and it dropping balls out of it, as they tend to do. And what they were asked to do was to simply kind of make some judgment about the trajectory that the balls would follow once the girl had dropped them. And they were asked to respond to that in two different ways, and they got both of these types of trial. So they they were either asked to make an explicit prediction about what would happen by placing dots on the screen to show what the path of the ball would actually be once it had been dropped, or else they were shown the path of the ball and asked to say whether they thought it looked correct or not, okay? So one is more kind of implicit, one is a more kind of explicit type of responding. And what they found was a very clear pattern, actually. With the explicit predictions, the answers got worse as children got older. So the kind of key thing to get right from this is that the trajectory of the ball is going to be forward. It's not going to be backwards or straight down if the balloon is moving, okay? It's going to be forwards. In fact, though, predictions showing backward responses increased between the three age groups that they had in this particular study, with the oldest kids making the most mistakes as far as this was concerned. So they were getting worse as far as explicit explanations were concerned as they get older, whereas the recognition responses actually didn't show anything of that kind of pattern at all. They were more accurate, and moreover, they stayed pretty much the same level of accuracy across the age range. So again, we got some kind of sense that if you're dealing with implicit responses, more tacit responses, it's relatively accurate, there's good knowledge. If you're asking for explicit ideas, then you're likely to find that they have problems and can't actually make appropriate responses, and indeed may even get worse as they get older. Okay, so what we've been working on most recently is the notion that one reason for this is perhaps that it's this because explicit understanding doesn't derive from the same source as this kind of observational understanding. And in fact, it perhaps more often derives from social experiences and from conversations which are being picked up in a different kind of way. So basically what we've got is a system that's doing some tracking of actual observations of events. And then we've got another system that's engaging in everyday conversations about things. And these two systems are perhaps not particularly well articulated with each other. And some evidence in that from some of our recent work on understanding of physical state change. I'm not going to test the audience at this point in time about what your knowledge of these different things is. But if you do know about the kind of basic physics involved in these state changes, though they differ in terms of direction and level of energy, the basic physics involved in each of these things is the same. Okay? So if you understand one in terms of the physical principles that are involved, you really ought to be able to understand all the others in the same kind of way. But in fact, that's not what happens. What we find is that that children are much better at understanding of melting than they are at understanding of freezing. This is true right the way through the primary age range. They're better at understanding freezing than they are at evaporation. It's really not till they're getting towards the end of primary school, at least ways in the UK setting, that they're understanding very much at all about evaporation, and forget about condensation. your average primary school kid knows nothing about this and really actually can't even recognize instances of it when it's happening. We've got some lovely tapes of children, often towards the end of the primary age range, being shown instances of condensation and describing the background. Oh, there's a wooden panel, and then not saying anything about the event itself. It's almost like it's invisible to them, which is really quite extraordinary. So that's very hard to explain in terms of any understanding of the physics that's involved, but it does reflect conversational differences. So kids both see and have conversations about melting events. Don't leave your ice cream in the sun, etc. It will melt. So they hear conversations about that. They do hear conversations about freezing as well. So let's put these things in the freezer and, etc. But they don't typically see events of freezing. So they're not getting the same kind of level of information as they are about melting. I gave this talk in Canada once, actually, about this work. And when I said kids don't see instances of freezing, they laughed. But I guess in some contexts you do see instances of freezing, but not in the UK, and I suspect not in Singapore anyway. And in terms of evaporation and condensation, they see these, but the processes happen typically over a kind of longer time span, so they're kind of less noticeable. And there's not really very much in the way of conversation about them. We don't talk typically about evaporation events or condensation events. The first two are the ones which have the kind of social utility, if you like. So basically, we're beginning to garner some evidence, and there's some other things there as well, that there's a kind of conversationally driven understanding that kids are acquiring, and that's separate from this kind of more tacit understanding that they're building up, really probably from quite a young age. And if that ERP study by Callahan and Rayner is anything to go by, it suggests that actually the failure to integrate these two different sources of information is really very, very commonplace, which means that that actually one big problem for science educators is that kids have a kind of a resource in terms of their understanding which can't be used educationally because they can't actually access it in order to actually be able to do that. So if we're going to take that kind of idea seriously, then what it suggests is that that what we should be doing educationally is trying to encourage events which promote the kind of accurate mapping of explicit concepts onto these implicit perceptions and make that kind of fusion between them that seems to be lacking generally. That's not entirely straightforward, however, for various different reasons. Firstly, we know from some good work with adults that actually if you're going to do that kind of integration work around evidence and beliefs and try and map the two things together, then that tends to be associated in adults with increased activity in the dorsolateral prefrontal cortex, which I think other people have said this afternoon, is linked to executive function, the kind of deliberate manipulation of information, and to working memory. And we know from other work that actually till children have got past the age of 10, they're not very good at doing this kind of thing. These systems are not particularly well developed at that point. It's also likely to be true that there is a kind of impact on this from poor inhibitory control. We don't have good data on this with primary school kids yet, but we do with secondary school children. From one of our current PhD students, Annie Brookman-Byrne, who's been looking at inhibitory control in science thinking in secondary school kids. And the notion here comes from other work by Masson and colleagues in Montreal, which indicates that actually when people become good at doing science, it's not that their concepts have changed, it's that the original concepts they held, the misconceptions that are typical of people generally, are still there, but they've been suppressed. And they've kind of put new concepts in place as an alternative to those. And what they've learned to do is almost automatically to suppress the misconception and replace that with the better, improved conception, which suggests that if you look at kind of counterintuitive instances of science reasoning, that inhibitory control should actually predict quite well how good children are at doing that. Those kids who are better at inhibitory control should be more likely to be the ones who've managed to suppress the kind of misconceptions and replace them with something more accurate that they might have been told about, taught within school. And what we found is exactly that kind of pattern. Inhibitory control predicts that kind of ability to deal with misconception problems at a better level. However, the problem is that again, this is something that younger children are probably likely to be less good at. And there may also be some other kinds of effects which we've not managed to kind of track too well previously, which relate to things to do with attention, with working memory abilities. There may even be, one hazards to go and guess, that there is some kind of unrecognized deficit in sensitivity that may be affecting some kids as well. We don't really know that, but it's kind of an intriguing kind of possibility. So there's lots of things going on that may make this difficult for primary school kids to do this integration work. And the final thing is that actually we also know, again, good work by some of our recent PhD students, that the language that children have is also a key predictor of their ability to kind of engage in these things, particularly their exposure to scientific vocabulary. Their understanding of scientific vocabulary is a very, very strong predictor of their performance during the primary school years. And of course, that exposure may widely vary from one child to another. Think about the importance of being exposed to number words for counting, but most kids will get exposure to those. That won't vary too dramatically. But variability in terms of exposure to scientific language varies enormously from one family, one different social context to another. So there's a big issue there about how much they might have tracking on that. So what this suggests is that if we're going to take this seriously in terms of primary school work, we should be focusing on promoting skills of observation and language, first of all. Don't worry too much about the controlled testing. Let's get the basics in place first. And that what primary school teachers in particular need to be doing is this kind of list of things here. They need to provide children with experiences which involve manipulation of causal events, so that's the observational side, which draw attention to the exact sequence within those. So this is about capturing that information accurately and probably moving on to describe them explicitly, so they're capturing those in language, and then providing then being able to connect those descriptions to explanatory constructs. Okay, so those are really likely to be the kind of key steps that primary school teachers in particular need to be engaging in when it comes to science learning. And in actual fact, we know the answer as to how to do this as well. Because collaborative group work in science, we've known for data that's been collected over the last 25 years or so, we know that this works. We know that actually if you get groups of kids to work together around predict, test, explain type tasks where they're making predictions, first of all, about outcomes, testing those out, and then trying to explain their observations. That kind of structured activity, we know reliably, and not just from lab work, but from real school work, big RCT stuff that we've done, this works. This produces robust improvements in children's understanding. And maybe this is because what collaborative group work is doing is providing exactly those kinds of key features that I've just been talking about. It provides a social context in which the observations are shared, and therefore there's good reason to actually talk about them. So observation is immediately being brought into contact with language simply because of the nature of the task itself. It also may be helping them to manage the informational load, the issue about executive function, being able to control all that, because it's no longer an individual who's having to do the integrative work. You've got 3 or 4 sets of eyes looking at this and trying to do the work conjointly. So the informational load is being managed. And also that maybe helps with the suppression of inaccurate ideas too, because if you've got 4 kids working together on a problem, if one makes an intuitive response, another is quite as likely to say, hold on, that's not what we should be thinking about here. So actually the kind of inhibitory control is kind of shared and externalized well. So what this suggests is that actually, in terms of what this kind of task is doing, it's a kind of combination of direct manipulation and dialogue together that's actually critical for bringing language and experience into kind of conjunction with each other, which is exactly what we kind of need to be trying to achieve. So if there's a kind of take-home message really for teachers, it's about organising good group work that uses these kind of techniques. But also critically, I think feeding in language and ideas at the right kind of point so that kids are being provided with the language to describe their observations and ideas about how they might actually explain them. and that needs to be kind of fed in at just the right point to actually help them work through the group exercises and understand those a bit better. That is likely then to support the kind of development of the core skills that children need to engage in doing science, and in particular to start to build up a sense of the theory-evidence relationship, which is really the kind of basis for them moving on to think about things like controlled testing and doing fair testing. Okay, thank you.